Okay, so what we have done just now, we introduced an area vector and we introduced the electric flux. And the electric flux is the electric flux density dot product with the area vector. So Gauss law, the flux of D through a closed surface. Okay, this is one of the most important topics of this module, and you must know this very well. Okay, so Gauss law, we can use it to find the electric flux density. Then we can use that to find the electric field. And for charge distributions of inside mediums such as free space, dielectrics, or conductor, or the mixture of the three, we can use Gauss law to find out the electric flux density, whether it is in free space, in dielectrics, or in conductors, or a mixture of the three. Before considering the law, before I tell you what Gauss law is, there's some preliminary topics you need to understand. Okay, so previously we talked about electric flux through a plane surface. We introduced an area vector. And now we're going to talk about closed surface. Okay, another type of surface that we commonly use in this topic, electromagnetism, is called a closed surface. Okay, so a closed surface, such as a sphere, is a closed surface. Okay, if you have a sphere, then the surface is fully enclosed. Cylindrical surface, so I put down here a back beam tin, okay, is also a closed surface. So any tin that you have top and bottom surrounding it, there's also a closed surface. Or another one is your soap bubble. So if you blow a soap bubble, that bubble is also fully enclosed. So all the surface touching each other. So these are called closed surface, and is important in electromagnetism because we're going to use that in Gauss law. So just now we talked about the surface area vector, and now we're saying about closed surface. So a circle itself is not a closed surface, as that is just a plane. A closed surface meaning that it's in three-dimensional and the surface is fully enclosed. So if you take every point of the surface, you go around it, there is no ends to it, or there is no discontinuity in the surface. So clear what's a closed surface? The surface of a sphere, like a ball. If you think of your basketball or your football, the surface is fully enclosed. Or if you think of your tin, I don't know, here I use baked bean, but here I don't know what you eat. What tin is more popular here? Maybe your chicken curry tin, or yeah, so it's fully enclosed. Okay, so you have the round, the cylindrical, and then you have the top and bottom. You can't spill anything out from the tin unless you open it. Same thing in a ball. The air can't come out because it's fully enclosed. You can keep the ball round. Or in the case of a soap bubble, you blow air into it, and then the surface tension of the soap create the surface so that it can enclose the air inside the bubbles. Okay, so that is what it means by closed surface. Very important. Okay, such as things like this. My sphere, closed cylindrical surface, or any irregular shape but have a fully enclosed surface, such as not soap. Okay, so irregular surface, okay, like a bubbles or something like that. So how do we set up about finding the flux of the electric flux density through this closed surface? So we have defined the electric flux outwards through a closed surface. So to find the electric flux outward through closed surface, we first split them into very small surface with a vector ds. So this vector ds just the same as the area vector we defined just now. Just now we defined a big circle with a vector s, okay, which is perpendicular to the surface. And ds is just a very small, tiny of that. Okay. So if we have an enclosed surface, we can break down all this surface into a very small surface, which we call a vector ds. And then to find the overall of this surface, we can do an integration or sum up all these small, tiny segments of my vector ds. Okay, so for example, if I have another one here, another one, if I sum up all this tiny little surface all around my sphere, then I work out the surface area of this sphere. Okay? And to do that, we can easily do it with limits of integrations. Okay, so in this example, so we have defined our vector ds, which is the area vector, a tiny, very tiny area of my sphere. If I break it down into a very small segment, and to find out the whole area of this sphere, I can do a closed surface integration of my small area ds, and that equals to 4 pi r squared. We know that the surface area of a sphere is equals to 4 pi r squared. So an example of a closed surface integral, we denote it with this circle here in my integral, and then we use a subscript there s to show that this is a closed surface integral. And ds, so in this particular example, that will be equals to surface area of the sphere, which is 4 pi r squared. And that will be the total closed surface area. Okay. So just now we define our electric flux, which is d dot s. So now it will be d dot ds, and that will be equals to a small amount of electric flux that going through that small little area. So if I have a big area previously, the electric flux will be d dot s. Now I string it down to a very small size, I call it ds. So my small electric flux, d phi sub e, will be equals to d dot ds. Okay, so back to our equations 2 just now, it was the electric flux equals to d dot s. And now for this tiny amount flux that's going through this segment, it will be d phi e. Okay. To work out all the electric flux that's going through this sphere, then we have to integrate it as well. Okay, so we do a closed loop integrations of d dot ds, and that gives us our electric flux that going through this closed loop surface. Okay, Okay, so this integration is actually quite complex, okay, because we have to basically work out the dot product between D and ds, and then imagine this here, my electric flux is going in all directions, so you have to sum up all these integrations, okay, of all the different parts that go through the tiny surface that I introduced. So it's okay, but for this equation 4 tells us that the outward flux of the electric flux density through any closed surface is equals to the closed surface line integral of D over that surface. Okay, so how much of the flux lines actually going through all this surface? So if we draw a closed surface, imagine this to be surface of any sphere if it makes it easier for you to think about. Okay, so if you draw a sphere around any regions, free space that has some electric charge, this surface will contain any material such as free space. It can be a free space, conductors, dielectric, or mixture. So if you think of it, if I draw a sphere, if this sphere contains some charge inside enclosed, so if this surface has an amount of free charge Q, so if I draw a sphere, if I have a charge inside there, so we talk about free charge. So we talk about D. Okay, so what Gauss law tells us? Okay, so this is Gauss law tells us that the total outward flux D through any closed surface is equal to the total free charge enclosed within that surface. So remember just now I asked you about the units. Phi is equal to D dot S, and we know that this unit has a charge of coulombs, and we know that this has to be equal to some form of charge. So what Gauss law tells us that if I have an enclosed surface, or if you think of it as your sphere, if that encloses some charge inside, then the electric flux has to be equal to that charge enclosed inside that closed surface. Okay, so go back to my diagram here. So if I have a charge here sitting here, Q equals to, let's say, 100 nanocoulombs. So if I do all this, so we said that this is equals to phi, my closed surface integral D dot ds, that has to be equals to that charge enclosed inside that sphere. Okay, and that has to be equals to 100 nanocoulombs, and that's what Gauss law tells us. Okay, so if that charge is outside here, then this charge is not enclosed in that sphere, then this integral will be equals to, so we said that the charge has to be enclosed inside that closed surface. So this is my closed surface. Okay, so if my charge is outside here, so now my charge is not enclosed in the surface, in the enclosed surface. My charge is outside. So what do you think this integral is going to be equal to? So just now it was inside. I said it's equal to Q. That's 100 nanocoulombs. But if I take the charge outside to that ball that I have, the sphere that I have, is now no longer enclosed inside it. So what is this integral going to give us? Anyone? Just doesn't matter if it's correct or wrong. What do you think? Just now it was inside. Okay, so Gauss' law tells us that the outward flux of D through any closed surface is equal to the total free charge enclosed inside the surface. Enclosed inside. So now the charge is outside. So what's the electric flux then? So what? Any charge enclosed inside? No? Okay, so no charge inside. So what is that integral going to give us? 0, correct. And that has to be equal to the charge enclosed inside this surface. Okay, so if I do my surface integral, it has to be enclosed inside that surface. So if the charge is outside, this integral is going to give us 0. Okay, so that's what Gauss' law tells us, that if the charge is inside that closed surface that you draw, then it will be equal to the charge inside that surface. But if there's no charge inside, if the charge is outside, then no charge is inside, it has to be equal to 0 because 0 charge enclosed inside. Okay? So it will be 0 coulombs. So this is Gauss' law. And to put it into equation, this is my Gauss' law. Closed surface integral d dot ds equals to q. So for simple structure, just now, if it's a sphere, okay, so if I have a point charge and if it's a sphere, then we know that the direction of my electric flux density is always perpendicular to the surface of the sphere. Okay, so d and then ds is always in the same direction. So d dot ds is simply equals to d times s. And then because if we center the charge inside the sphere, then every point of the surface have the same magnitudes of d. So d is constant all over the surface. And therefore this integral becomes simpler because d is constant, you can take it out of the integral, and that is simply equals to an integral of the surface area of the sphere, which we know that is equals to 4 pi r squared. Okay? So simple structure like this can be easily solved, but if I have a charge q, if I draw a irregular shape around my charge, that can still be solved, but it's very complex to solve because my d at this point here is not the same as the d at this point because it's of a different distance to the surface, and then therefore this integral is very complex. Okay? So it became very difficult to solve. So we only do simple structure that have symmetrical and also of a constant electric flux density of the surface. So there are some simple surface that we can use that give us or simplify this integral. Okay? And the charge is just a superposition of all the charge inside the enclosed surface. So remember, this is free charge. Okay, because it's D, so D only depends on free charge. So if you want to do the same for electric field, then it becomes more complex because the electric field depends on free charge and the polarizing charge. And therefore, you have to do a superposition between the two, and it becomes more difficult to solve. And therefore, that is the reason why we introduced D in the first place.